In experimental physics, precision is everything. Whether researchers are manipulating electron beams or calibrating sensitive compasses, they require a perfectly uniform magnetic field, a volume of space where the magnetic force is identical at every single point. The simplest way to generate a magnetic field is to pass an electrical current through a single circular loop of wire. But this setup has a strict limitation, dictated by the Biot-Savart law. The magnetic force is highly concentrated right at the exact center of the loop. Tracing the central axis of this wire loop, an overlaid bell curve graph shows the magnetic field peaking sharply at the center and dropping off on both sides. Placing an object slightly off-center causes the experienced magnetic force to plummet rapidly. Because the spatial variance is so extreme, a single loop cannot provide the stable, controlled zone necessary for a reliable experiment. These notes detail an elegant solution, a setup of two identical coaxial coils separated by a distance equal to their radius. With current flowing in the same direction, the magnetic induction in the region between the two coils becomes completely uniform. We can see this exact setup in this 3D model. We have two coils with a radius defined as r, spaced apart by that same distance r, with the current I moving in parallel. This is the Helmholtz coil. It demonstrates how strict, simple geometric constraints can resolve complex physical variations without requiring intricate hardware. The mechanics of the Helmholtz coil rely on the principle of superposition. When multiple magnetic fields overlap in space, their values simply add together algebraically. If two identical coils are placed farther apart than distance r, their combined field line creates a distinct valley. The fields decay too much, leaving a weak central zone. Moving them closer than distance r makes the curve bulge upward into a sharp, single peak. In this scenario, the overlapping fields reinforce each other too intensely at the center, creating a completely new, steep gradient. To achieve a flat, uniform field, we have to find the precise mathematical inflection point, where the decay of the first field perfectly compensates for the rise of the second. The top right diagram visualizes this inflection point. Coil 1's lower yellow curve decreases to the right, while coil 2's curve mirrors it, increasing to the left. Spaced exactly distance r apart, their slopes perfectly cancel out, creating the flat B overall combined curve. That wide, flat plateau between the dashed lines represents a volume of space where an experiment can be moved in any direction without experiencing a change in magnetic force. To mathematically prove this uniformity, we evaluate the system at its most symmetrical coordinate, the exact dead center between the two coils. Since the total distance between the coils is r, this midpoint sits at a distance of r divided by 2 from each coil. Because the coils are completely identical and symmetrical, they contribute the exact same amount of magnetic force to this specific coordinate. This yields a highly efficient algebraic shortcut. To calculate the total magnetic field, we just find the field generated by a single coil at distance r over 2 and double it. By leveraging the spatial symmetry of the system, we can bypass spatial calculus and solve the problem using simple algebraic superposition. This midpoint rule is written out explicitly at the bottom left of the source notes, setting the Helmholtz field equal to twice the field at x equals r over 2. To see how this works, we stop at this standard formula for the magnetic field of a single loop along its central axis. The equation uses the variable x to represent the distance from the coil. Following our midpoint rule, we substitute the x squared in the denominator with r over 2 squared. Expanding that term mathematically gives us r squared plus r squared over 4. Combining those terms simplifies the expression to 5 over 4 times r squared. Applying the 3 over 2 exponent to this fraction structurally alters the constants, yielding 5 times the square root of 5 over 8. The deliberate constraint of placing the coils at a distance equal to their radius directly forces these specific irrational numbers to appear in the denominator. Looking at the final boxed equation in the notes, we see the result of multiplying that single coil expression by 2. This operation isolates a specific fractional constant at the front, 8 divided by 5 times the square root of 5. The remaining variables define the physical inputs: mu0 for the magnetic permeability of space, I for the current, r for the radius, and an n multiplier to account for the number of wire turns in the coils. This 8 over 5 root 5 constant represents the unique mathematical signature that occurs when evaluating the magnetic field at exactly half the radius distance. Ultimately, the Helmholtz coil design suppresses the chaotic spatial variance of electromagnetism by relying on a single, perfectly calculated geometric ratio.